advisory standing gets to pass down legislation to us, or in various forms. So anyway, in this figure, the black stuff here shows the centralized generation as we have today in the grid. So in the grid, we mostly have centralized generation that is produced mostly in the 5 to 25,000 volt range. And then it's stepped up using a transformer right here. It's stepped up to a transmission voltage. The voltage levels are given here. This is not too big. I don't know how well you folks back there can see this. Okay. Is there a way we have, because the screen is big enough, that blurs it, but this is about as big as it gets, right? Okay. Sorry. Okay. So anyway, I'll read this out. Electricity is transmitted over large distances in the form of three-phase AC at voltages of 138 kV, 230 kV, 345 kV, 500 kV, or 765 kV. We don't have that many 765 kV lines in the US yet. We have a few, not many. They are thinking of building some more. We don't have any megavolt lines yet. I know there are some countries in Asia that have started building megavolt lines. I think China has built the first megavolt line. I know one other country has done that, fail to recall which. But we haven't gotten that far yet. So anyway, we transmit at high voltages for two reasons. One is that way we lose less power in transmission. And the second thing is, we are able to maintain the voltages. If we transmit at lower voltages, then the voltage tends to drop by the time it reaches the sender, the receiving end. So then we come down to the distribution system. Okay, all the green stuff is distribution system. So the black stuff is generation, blue is transmission, the green is distribution. There we step down the voltage to lower levels, typically 69 kV and below, and send it to different kinds of customers. So we could have large industrial or commercial customers at higher voltages. So they do what they need to. We send out the system sends out the power to them. They step it down to the voltages they need to use it at, and then we have what are called primary customers, which are also relatively larger customers. Primary, in the distribution system, the term primary is used to denote customers that take three-phase power. And then we have secondary customers, like us, residential customers. Secondary is used to denote single-phase power. So the stuff you get out of the wall socket is secondary. So what happens is single-phase power is sent out to you at between 4,000 to 7,200 volts. There's a pole-top transformer that steps it down to 120 and 240 volts. So it's like there's a center tap at 0, then there's a 120, and there's another 120 on the other side, displaced 180 degrees in phase. So across the two outer terminals, you get 240 volts, which you use to drive air conditioners, electric dryers and things like that, cooktop. Everything else gets 120 volts. So that's what comes out of the wall socket. So that, in a nutshell, is describes the primary, the basic functional parts of a power system. And here's a quick description. So in the generation system, we produce power, three-phase power at 4 to 25 kilovolts. It interfaces with the transmission system through what are known as generating stations, where voltage is stepped up to 115 to the 765 kV range. The transmission system is a meshed network. It has some loops. Okay, it's not radial in that power does not necessarily flow in single direction all the time. That's why, because it's meshed, it's also called the grid. And I'll come to that on the next slide. transports three-phase power at 115 to 765 kV, interfaces with other transmission lines, sub-transmission lines at switching stations. And switching stations connecting to sub-transmission lines step down the voltage to the 20 to 69 kV range. And then the third part is the distribution system, which is mostly radial in nature, which means the power flows out in one direction through the feeders. There are no loops. There are some distribution systems with loops. Urban distributions, very dense urban distribution systems sometimes have loops, but most distribution systems in the United States do not. Okay? Through primary, that is three-phase, or secondary, that's single-phase feeders to customers. And the distribution system connects to the sub-transmission system through the distribution substation, where the voltage is stepped down to 33 kV and below. So here's a figure I drew to sort of mark out the boundaries. These are the centralized generation that we have. Okay, they form the generation system. They are at generating stations. They connect to the grid, which is the transmission network. Notice I've shown one loop, but in general it's much larger than that. Okay, and when we want to tap power out of the transmission system, we use a sub-transmission line which brings out power to the distribution system. So the distribution system has primary and secondary customers. Midway we can have sub-transmission customers, that is customers that need a lot of power. We can connect them to the intermediate high voltage, that is between the transmission and the distribution voltage levels. We can give them three-phase power at that level to do what they choose with it. So that in a nutshell is the grid. So this is the grid or the transmission system, and it's separate from the distribution system. When you talk about utility companies today controlling the distribution system, they are usually in charge of both the sub-transmission and the distribution system. Like if we were to talk about Consumers Energy, Consumers Energy is a generating and distribution company. What that means is, back in the old days, they used to control everything, generation, transmission, distribution. But with the restructuring of the industry, when they deregulated, they were not allowed to hold on to all three. Transmission was opened up to open access. So it had to be owned by an independent body. So they had to sell off transmission. Now they have generation and distribution. So that pretty much should explain what the grid is. Okay? So do we need a smarter grid? The fact is, if you look at today's grid, okay, which does not yet fit the definition of what we call a smart grid, it is extremely smart by itself. Okay, if you think of the extent to which we take it for granted today, we flip a switch and we take it for granted that the light will come on. Okay, and trust me, that doesn't happen in a lot of other countries. Okay, we are very fortunate that we have a system that we can take for granted. Okay, it's a very high reliability system. Okay, it has also been built to be extremely smart. Okay, it's got very highly sophisticated features. We've got monitoring and control, all kinds of monitoring and control functions for normal operation. We've got all kinds of protection from abnormal operating conditions, so that something really nasty does not happen to the system. Okay, but then there are other directions in which technology has evolved, particularly in the communication and information technology areas, and there was those that realized that if we could use communication and information technologies to increase system-wide awareness, it may enhance the performance in several areas. I say may because if it's not done right, it can actually adversely affect the performance. Okay, but if it's done right, it can actually give us higher efficiency, higher resilience in terms of stability, reliability, security, and automated recovery from anything that goes wrong with the system. Lower consumption of fossil fuels, and lower pollution. We can get all these benefits from the smart grid if it's done right. So what is the smart grid? It is actually what we call in other realms the cyber physical system. We have the physical layer, which is the grid as we saw it in a couple of slides ago. Okay, it's got generators, it's got centralized generation, it's got a transmission network here, and then we have a sub-transmission line going out into the distribution system. We've got a primary distribution, we've got secondary distribution. Okay, normally windmills, if we have wind farms, we plug them into the sub-transmission system. Okay, if we residential solar, plug-in electric vehicles, they all plug into the secondary distribution network. So I've got all those, and I'm calling this the physical layer, where the energy actually flows. And then we've got a second layer on top of it, which has all these communication abilities, all these things that I've shown, little radio towers sort of things. These are symbolic representations of communication nodes. They may or may not be wireless, okay, even though they are getting more and more wireless these days, but they may or may not be wireless. They don't have to be. We can use wired communication channels as well. Okay, and then they communicate between themselves if necessary, and certainly with the cyber layer. Okay, where we have a network of computers. Okay, connected through the symbolic Ethernet backbone. Okay, we have data servers and massive. We don't have them yet. Okay, we'll have to have massive data processing ability. Okay, and this layer communicates with this. Okay, and the jelly between the two slices of bread that you see here is basically two-way communication signals and monitoring and control actions. That's what holds them together. So this is a cyber layer. Okay, so this is a cyber physical system. And what does a cyber layer have? It has data acquisition capabilities, decision-making capabilities, and supervisory control of the physical layer. And what does the physical layer do? It is the electric grid, an interconnected system of generation and storage, transmission and distribution, and loads. Okay, and measurement data is collected by meters, sensors, and synchrophasers. Meters, well, today's meters, the old-fashioned meters, do not have the communication capability, so they are being replaced by smart meters, which, let me tell you, they don't cost that much. Okay, they cost about $200. I was told of utilities that are actually charging some customers the $200 connection fee for the smart meter, when they are actually going to benefit more from it than the customer will at the end of the day. Okay, so be aware of that. Okay, but that has communication capabilities built into it. So that's meters and voltage and current sensors will be installed at the distribution level. What are synchrophasers? Synchrophasers are phase measurement units that send phasor measurement units. What they measure are magnitude and angle signals mostly for voltages. Okay, at various parts of the transmission system. Yes, there are some utilities that are sort of going overboard. They have a lot of money to spend. They're putting this on the distribution system. In my humble opinion, it doesn't make sense to put them on the distribution system. Okay, I know Excel Energy in the Denver area is putting in like 5 or 6 synchrophasers in the distribution system, which I think is extravagant. Okay, but because they cost between $10,000 and $30,000 a pop, each synchrophaser installation. But if we have many of these on the transmission grid, what it does is they take voltage and phase measurements, put a timestamp on them, and send it back to this layer, so that this has a set of coordinated measurements, which gives it a good wide area awareness of the system. Otherwise, what happens is some of the signals from here could be traveling over wires, some are lossy lines, some of them could be wireless. They all arrive at various points here at different points in time, so you don't know if they are, the measurements that you have at any given point of time correspond to actually the same point of time in, when we are talking about operational time. Some could have had longer latencies, some shorter latencies, and so on. But with the timestamps, we are able to synchronize the measurements and make the necessary calculations and decisions. So those are useful devices, but also expensive. So anyway, this in a nutshell explains what the smart grid is. It's basically a cyber-physical system. What are the expected benefits? The utilities expect to gain from higher reliability and security, which comes from higher situational awareness. If they have a wide area measurement system and a wide area control system, they can better coordinate the operation of their assets in a way to maximize their utilization and thereby defer capital spending on expansions. Properly coordinated operation will lead to reduced operation and maintenance costs and efficient power delivery. Potentially, customers can also see some benefits in the form of consumption management, cost savings. You've heard of demand response. Okay, customers, if they know if they get to know their own spending patterns, they can make sure that they are more effective. Okay, ability to connect distributed generation. So far, if you had, well, nowadays in some areas the law allows you to connect things like solar panels to the grid and sell power back to the grid. Okay, but if you had other things, like if you have a backup generator in your backyard, for instance, that sits there gathering rust for the most part, except when you have a power failure, okay? The only way to connect to it is by disconnecting from the grid, okay? Because you don't have a way of synchronizing it to the grid, and that is one thing. The other thing is, if the utility sends out a crew to fix the line, they don't want that part of the line energized, and if you've got something connected to the grid, they are not aware of the fact that that part of the line is energized. So there were safety issues and things. So, but now rules are, protocols are being designed that allow you to connect distributed generation to the grid. Everything from rooftop solar to, that $500 backup generator that you have sitting in the backyard, if you do. Okay? Convenience from advanced meters, enhanced business consumer service, reduced industrial commercial cost. That arises from the fact that they have, if they are able to get, if an industry which has a lot of motors, for instance, are able to get price signals in a coordinated way, then they can make sure that they are operating more efficiently with regard to price. They operate their machinery as far as possible when the prices are lower. So their costs are reduced. So there are various benefits that we won't go into detail today. I think I've taken my 20 minutes, so I'm going to go through the next couple of slides very quickly. Technology, okay? What kind of technology goes into smart transmission systems? PMUs, I just talked about them. Flexible AC transmission systems, these are devices that let you control how power flows through the system. Yes, they are governed by the laws of physics, but if you can tweak the parameters of the system slightly so as to accomplish a little more control over the power flows while still respecting the laws of physics, why not? So flexible AC transmission systems let you do that. Dynamic rating of transmission equipment, what that means is actually transmission equipments were rated at the time they were designed based on worst case operating conditions. But if you're able to monitor operating conditions through a smart communication, measurement and communication system, then you may be able to calculate in real time what the actual capacity of these devices is and of transmission components is. And sometimes you can squeeze an extra 30% capacity out of them if the operating conditions are favorable. So that helps you because it defers capital spending. Okay, monitoring and control devices. Okay, the challenge is coordinating a very complex and widespread communication network and enormous data management and optimization capability is required. And the data management, the more they think about it, the more complex it seems to them. So they are still working on it. They are developing standards and so on. But it is a staggering problem. What kind of devices do you see in technologies do you see in smart distribution systems? You see advanced metering infrastructure, distribution automation devices that, as you know, in today's utility, if you have an outage, if you do not get power, the utility doesn't know until you call in. Okay, but the fact is, it's worked reasonably well. We've survived, and it's kept the prices low. All right, but now we can put in automation that automatically senses and locates these faults so that they can fix it quickly, and to some extent they can even fix it automatically by isolating small areas around the fault and bringing everything back to service very quickly, even without sending out crews. Then they can send out crews to fix the fault only in the affected area. Demand response, how has to do with customer and consumer behavior in the presence of prices. We pay a fixed rate now, but what if that were to change? And that is going to change, because during peak hours, the utility has to pay a lot more for energy than we do. So why shouldn't they, they'll pass that on to us. Okay, at the same time, during off-peak hours, they have to pay a lot less, and we should be able to benefit from that. So, right now the only way we can take advantage of, or we can participate in anything like this is when I tell my wife, please don't turn on that dishwasher at 2 in the afternoon. Okay, wait till 8 or 9 p.m. before you turn it on. Okay, but in the future there will be other price signals communicated to us. There will be smart devices that automatically sense the prices, and you can say that, all right, don't turn this on until the actual price comes down to, say, 6 cents a kilowatt hour. Don't turn it on if it's at 50 cents a kilowatt hour, right? So, so demand response is, if it's done right, it's a good thing. Plug-in hybrid vehicles, we've heard about this happening. People are concerned about this. Okay, so it must enable automated sensing, protection, restoration, okay, and other things. Adoption of technology is always a challenge too, especially at consumer level. Okay, and again we have complex communication and data management issues in the distribution system. Okay, the other thing is distribution system has way more components than the transmission system. So how do we control the costs if we have to invest in the distribution system? Here's a list of how smart appliances can work in the home. Okay, smart appliances respond to price signals, resulting in several cost-saving opportunities like operating during off-peak, low-price periods. Refrigeration, water heating, and HVAC systems can benefit from longer on times during off-peak periods. Okay, operation of appliances and heating and cooling systems can be staggered, so the peak is controlled. If all air conditioners on the same feeder don't kick in at the same time, it helps, right? And the utility can control that. And consumers who adopt these technologies, because these are modern, and more efficient technologies, they end up using technologies that are more environmentally friendly at the same time. So anyway, the grid is a very complex system, and the smart upgrade comes with many benefits, complex challenges, and of course, high cost. And in the next 3 presentations, we'll show you how we plan to bring the smart grid to MSU. Thank you.